Welcome back. Let's do another practice exercise. So I have extended our player Smali file a little bit and now even more because we already talked about those floating point numbers. So I added one to get also practice on this one. Okay, let's go. Therefore I switched to the Ubuntu VM and I have attached you the file as an APK to download. I've already got this over here in our downloads directory. This one, and I put this into apps. And let's make a new challenge. Practice Smali. Okay, let's decompile this with the APK tool. And then we will have a look at the Smali code, and afterwards I show you the original Java code, and also if you take a look into JDX, what's different. I guess there is something different regarding to optimization of the compiler. But let's see this at the end. First, let's reverse engineer this application. Okay, so we've got this over here, Practice Smali. I'm opening this whole directory once again within Visual Studio Code. There we go. And here we have our player.smali. We change to Java and we keep clicking these annoying pop-ups. And here we go. I'm going to make a screenshot of this, put it on my graphic tablet, and then we will analyze it there. So I see you in a few seconds. All right, here we've got this file right now, and you can see this file is massive. But we do this step by step, and we go through this each instruction after each other. We also include what we've learned in the last video. Therefore, we do not dive into a method over here. We start at the beginning of this file. And by going through this file, we will reconstruct the Java source code out of the Smali code over here. Therefore, let's go. What do we have here? We've got our class public, and then we've got this capital L, which means we've got a class reference. This reference ends at the semicolon over here, which means we've got a class named player. Let's write this down. Class player. Alright, then we've got the superclass over here. The superclass is Java-lang object. This means our player class is a subclass from Java-lang object, but we are not extending a certain special class over here. This means we are already at the end regarding to the class definition. I guess I wait with the end because we might scroll down a little bit. Alright. So we also get this one, and this one is simply just the name player.java of the file. So this was the header, not that hard. All right? Okay, then let me choose a different color and we make our way through this one. We've got our hashtag over here, which means we've got a new separator. In this case, static fields. So now we've got our static fields for this class. And we only have one static field because here at the end, we already have a new separator regarding to the instance fields. Okay, let's see what static field we've got. We've got public static lives. This is the label. So our static field is lives, and lives is from type integer. Okay, we can simply write this down exactly the same way. So we write this down as public static int, and then we have lives. Alright, we can see no register, no initialization value. So simply just this public static int lives. Okay, next, let's have a look over here. Here we have now our instance fields. And we've got two instance fields. One is power and one is shield. Power is from type integer and shield is from type? Correct, Boolean. Also, let's add these information. So we've got int power and we also got Boolean shield. All right, then we get to this one. These are all our instance fields. Next, we've got the direct methods, which means we've got constructors and private methods. In this case, we skip this because This constructor contains some object references and we didn't talk about this one yet. We will learn this in a few sections, but for now let's skip this because I guess we still got lots of stuff to do, okay? So these are our private methods. We do not have a private method. We only have this constructor, but we skip this. Okay, then I need to scroll down a little bit. Let's do it this way that we can still see our instance fields and yeah, therefore we just add our code now underneath. Okay, what do we have right here? We've got now our virtual methods, which means we've got now our public methods. Our public method is named addPower. So we've got a public method addPower. addPower. This method addPower has now 3 parameters. New color, this one. We've got 1, 2, 3, all from the type integer. Okay, but now let's stick to the register labels. So in this case, we are using P1, P2, and P3. We know our P0 is reference for this object. Therefore, our parameters start with P1. And by keeping or sticking to the register labels, we do not have to look things up in the code. Therefore, we can execute each line after each other like the CPU does. Regarding to the parameters, yeah, of course, we already got them here. But regarding to the local variables or local registers, we would have to look them up if we want to address those labels immediately. And this is something we do not want to do. My approach when I do my Smali reverse engineering is I go through this each line after each other. And yeah, let's try this out here. All right, so we've got 3 parameters, all type integer. So our first one is int p1. Next one is int p2. And then we've got int p3. Okay, and we can also see this one over here. We've got the return type from type D. Do you still know what this capital D is? Correct, it's double. So we are returning a double value here. All right, we already got our function definition over here based on 1 line of Smali. Isn't this amazing? It absolutely is. All right, now we've got this locals 5. And this is exactly what I was talking about. In our case right now, we just take as node, we've got 5 local registers. 5 local regs. Which means we've got register from V0, V1, V2, V3, and also V4, because we start counting with V0. We do not do this in the parameter tabs because P0 is a special register reserved for the this object. All right, so we got this line also. We also got these, and yeah, if we want to, we can address those labels here. So we can say P1 is A, P2 is B, and P3 is factor B, and this one here is factor. Okay, let's do it in this way. So then we've got this one, and this one. Now we've got our first real Smali instruction. Yes, I would call this way. So we've got const /for v0 0x0. Do you still know what this instruction does? So this instruction stores the value 0 into v0. But it only stores 4 bits of this value in v0. In our case, it doesn't matter because 4 bits of 0, 1, 2, 3, 4 is still equal 0. But we are limited to 4 bits. In this case, we cannot store a value, for example, like 20 in this way. We would have to adjust this const over here, this /4, to something like const /16 or remove this part 4 if you want to override or patch this application, this instruction here. Okay? All right, for now, let's get rid of this one. So there we go. And we simply write this down. What does instruction do? We've got v0 is now equals 0. Okay, Next one, we've got this over here. And here we can see the register, this V0, is now being addressed as a variable. And this variable is named sum, and it's from type integer. Okay, we make this node over here. So we've got a sum, let me clean this up real quick. So, all right. So we've got sum from type integer. So we've got int sum, and sum is equals 0 based on this instruction before, this one over here. All right, and by doing this, we do not have to look this up first. So we go through this each instruction after each other. Slowly progress through the Smali method over here. Okay, and this is the approach I like to do. So go through this instruction after each other. And therefore we stick to those registers over here. And we take notes of the Java code on the right. All right. Next, we've got this const dash white v1. Then we've got this really strange looking value, but we also got this hint over here. So we do not know what const dash white does. And this is something we have to look this up. Regarding to the first section, we know this value gets stored in v1. This value gets stored in v1 over here, in this register. And this value is represented by this strange hex representation. This is a floating point number, and therefore, we have our signed bit, we have our mantisse, and we have our exponent. We do not care about this because we've got the value right here. But what does const dash white do? Because this is important that we look up instruction where we are not sure what they are doing. This might affect our result in this register later on. So let's have a look. Therefore we go into our Ubuntu VM. And I really hope you have bookmarked your Dalvik opcodes page. So let's see, const dash white. And put the integer constant into Vx and Vx plus 1 registers, expanding the integer constants into a long constant. All right, what this does is, let me check something quick. Okay, we have to take care, let's see, we've got this lit 16. In our case, we've got a const value, let's see. Do we have other const byte instruction? No, okay. So let's get back. And yes, okay. It's within the description. There we get this crystal clear. So we've got const dash white v2, and then we've got our long variable over here, or our double variable in our case. And here we can see we are putting 64 bits into Vx, because otherwise we would have this dash 32 declaration at our instruction over there. Okay, so now we know we are definitely putting 64 bits into our register Vx. In this case, it's v1. There we go. All right, so let me clear this up a little bit. So, okay. So we can make this as a node. 64-bit, at least this value here, into our register v1. Okay, let's write this down. v1 is equals 2.3, and we do not care about this one over here. And okay, yeah, that's all we know for this instruction over here. And the next one, we can now see, okay, we've got v1, and v1 is now also a variable named bias, and it's from type double. So we've got a double bias, and this one is 2.3. So we also got these two. Then we've got our add int instruction over here. Add int. And what add int does is it takes p1, adds it to p2, and stores the result into v3. So we've got a v3 is equals p1 plus p2. And here we can see we haven't used v3 yet. Therefore, let's keep this open for now. Next, we can see v3 is still not referenced as a variable, but we do not care about this because we go through this code each instruction after each other. Therefore, if v3 is never being assigned to a variable, we do not care. We are just interested in the value or the command over here, what this instruction does. And in this case, we know we are adding a plus b and store this into v3 in this register. And this is why I like keeping the approach or sticking to those register values. You do not have to bother about, oh, does it now become a variable or not? Might it be? Might it not be? Who knows? We don't care, okay? So let's scroll down a little bit and move on in the code. What we've got here, we've got now mul-int, and yeah, this instruction is new. It's pretty clear what this instruction do, but anyway, let's look it up, because then we can be sure and we do not make dumb mistakes where we have assumed that this instruction is doing the following thing and at the end it does something else, something different. Okay, so let's look this up real quick. I mean, it's super fast. Okay, if you have your to type your password, it takes a little bit longer, but it's still super fast. So we're looking for multiply int. This one over here. Multiplies, we set with wy and puts the result into vx. Oh, I think I have encountered something. Yes, this one over here seems to be a mistake. This seems to be a typo. I would assume this might be vy. But nevertheless, this website is amazing. Okay, let's write this down. So we've got vx equals, then we've got vy multiplied by vz. Regarding to a multiplication, I guess regarding to the arithmetic operation, yes, it doesn't make a difference if we multiply this with this or vice versa. So if we swap those parameters, this doesn't really matter. But I'm pretty sure it should be in this order. Let's see what we've got here. Yes, okay. Here we also got this typo. And yeah, we do a multiplication from two registers and store the result into vx. All right. That's what this instruction does. And good that we looked this up, because then we realized there's a little bit of a typo over here. So let's get back. Okay, we are multiplying v3 with p3 and we store this result back in v3. Let's write this down. So I'm gonna make a slight note where we are in this code over here. v3 is equals v3 multiplied by p3. We can now also do some fancy math and replace v3 over here with this, but yeah, let's do not do this. So we do this each instruction after each other and we execute and insert our values later on in the exact same way, okay? So please do not try some math operations and yeah, get rid of parameters or values. All right. So next, what do we have? We've got end local v0. This is interesting. I guess I also didn't recognize this variable in this way right now, but this seems to be the end of v0. So we are not using v0 at this point anymore. Nice. And for me also super interesting. What's also nice, we can see this register v3 gets now reused. We get now v3 aligned to sum. Super interesting. And we also see this integer type over here. So of course we do still have our int sum, but now our v3 is going to be referenced with sum. Okay, and at least at this point, I mean, I didn't prepare it in this way, but it's nice to see it over here. But at least at this point, I would be super confused if we stick to those variable names over here. Regarding to the registers, I mean, we do not care. We move on with our code and yeah, we really do not care about if this v3 is now sum or v0 is sum. We're just interested in the values these register holds. And therefore, I really like this approach regarding to sticking to those registers even more. Okay, so let's move on and let's see what we've got. Next, we are adding int lit8. So we know this is 8-bit. And we are adding v3. Nice. We are adding v3 with -1, and we store the result back in v3. So what we've got here is we are not adding two values, we are subtracting values. And I'm not sure why the compiler has chosen this instruction, because there's also an subtract int, I guess. Let's look this up. Yeah, it's just above this instruction over here, subint, calculates vy minus vz. So this might be regarding to compiler optimization. The compiler or the program might be faster if it adds -1 instead of using the sub instruction. Super ridiculous, but okay, this is what the compiler does. It's funny to see this in this way. All right, so let's write this down. v3 is now v3. We can write this as plus -1. And now we have our fancy math operation here. But for me, this is a little bit confusing, so let's do this in a different way. Let's write this as it is. All right. Okay, next we've got a new instruction. Ooh, what might this be? No one knows, I guess. So we've got div-int p1, v3, p2. So you see, with those registers, it's now getting a little bit, let's say, complicated or confusing. But if we insert our values afterwards and go through this step by step, you will see it's not that hard to execute this code afterwards on our paper. So let's see this instruction first. Okay, div-int, there we've got the correct order, yes, result, all right. So divides vy with vz and puts the result into vx. Let's see, div-int, we've got p1. So we are at this instruction right now. p1 is equals v3 divided by p2. And we can try to insert our labels over here. So let's see. P1, I have to scroll up. P1 is A. A is equals sum, because sum from this point is now in register v3. We can also write this here. Sum is equals sum minus 1. Okay. We were at this point. Sum divided by p2. p2 is b. Okay. Yes. All right, next we've got this instruction, XOR-int. XOR, let's look this up. XOR-int. And here we can see we've got this to address. We are not looking for this one. We are looking for this one. And let's get rid of this. Calculates vy XORed with vz and puts the result into vx. Okay. So we've got v0. v0 is equals v3 XORed with p1. In this case, v0 is now, let's scroll up a little bit. Also interesting. We can see right now we are using v0 as a register. But at this point, we have switched from v0 to v3 for the register or the label sum. And this means we have now a new free register, this one over here. This one is now reassigned and newly reused. So this is a whole new register over here. Therefore, we cannot make a label for this over here. Again, this is why I like sticking to registers and not always, try to adjusting those variable names, because in this case, we do not have a variable name for this one right now. We know this one is sum and we know this one is A. Was this A? Yes. Okay, so we know this one is sum and this one is XORed with A, but we do not have a label for this one right here. So we have to move on in the code. So the CPU simply executes this command, sum XORed with A and stores the result into V0. By the way, if you do not, or if you are not familiar with the XOR instruction, I have attached an own section within the cheat sheet of this course document. So within there, I describe some XOR operations, what XOR does, and why it's really useful and helpful to understand XOR. Because XOR is used a lot regarding to cryptographic functions, strange cryptographic functionalities, which are written by the developer itself, and also regarding to assembly, for example, for clearing out registers and things like this. So the instruction itself is not that really complicated, but it's super nice if you understand or if you know about the tricks you can do with XOR to get some cryptographic keys back and things like this. Therefore, please have a look at these slides, and I might be also creating an own bonus section regarding to XOR. Alright, please look this up in the material. Also in the bonus video, I'm pretty sure I create this one. And if you have questions anyway, then feel free to write me a message about this, okay? Alright. Okay, yes, interesting. So now we've got end local v3. So our sum variable from type integer is now finished on the register v3. It's not anymore holding the sum. This is what this instruction do. And here we can see restart local v0 sum from type integer. So here we can see we are reusing this register v0 as the sum variable. This means v0 becomes sum back again. All right, and at this point we know, okay, this one is also sum, but a little bit different. So this one in this case is some kind of placeholder. So we've got a placeholder for sum, and afterwards we recycle v3. So this register gets recycled. And then we create our sum over here for v0. Okay, if you stick to those labels, it's getting a little bit complicated. Let's clean this up. And let's write this down as the instruction tells us. So we've got this one over here. Okay, this was this part. And then we've got return local v0 to sum. This one is this part. But these are not real instructions, so we do not make progress within our code right now. Until, so we also got this one, yes, until we go into this one, because now we can see int to double v3 v0, okay. So let's check what int to double do. Int to double. Converts the integer in vy into the double in vx and vx plus 1. And this vx plus 1, by the way, and this means if the value doesn't fit into one register, we are using two. So let's say we are using v3, then this will be v3, this vx, so v3 is vx, or vice versa, let's say it different, vx is v3. And then we are also using vx plus 1, which means we are also using v4, the register. And I guess you can find this, let's see, in the description. Yes, here you can see this plus 1 means we are using two registers to store this value. For example, if we have a larger value which is going into a smaller register, then we split this value up into two registers, for example. Okay. So what do we have right here? Our instruction says we are converting v3 to v0. Sorry, I have to look this up once again. Converts the integer in vy. So this one is the integer to a double. Okay. So this one is the integer, and this one is the double afterwards. Yes, this makes sense. Okay. And let's try to write this down. This is a little bit hard. Let's see. So this one is int and this one is double. So we've got v3 is double v0. Okay. And this means v3 is also from type double. But let's not write this over here. Let's write this downwards here. Okay, so this should be, this should be fitting. All right, and then we've got this return byte v3. Let's see if we also find this instruction over here. Return dash byte. Return with double or long result in and so on. Okay, so we are returning v0 and v1 in this register, in these registers, and this is just the return of a double or a long value. So we are returning v3 over here. All right, and this is our code. If we get back on this, so this is the method add power. This is what add power does. And we can now simply insert some values over here. And then we can go through this code over here and check what's the result at this point. Let's see, maybe we do this. Yes, we make this or we do this for the next section. And there I also show you then the Java code. We execute this method with the values we are inserting right here. And then we have a look at the Java code. What the Java code puts as a result out of this function and also what we got out of this function. And yeah, let's take some values already that you can start practicing if you want to. As values, let's see. We take for a 1, 3, 3, 7. Yes, these are our values we are inserting or which we are using to call this method. 1, 3, 3, 7. 1, 3, 3, 7. Yes, let me get rid of this pink. So let's write this once again. 1, 3, 3, 7. I hope it's working in this way because I didn't check the code regarding to overflows or things like this, but I'm not sure what we are doing with B. So B is P2. Let's check this code really quick. We've got P2 over here. We are dividing, okay. So therefore, if B would be 0, this would be bad because we cannot divide by 0. Yes, but the rest looks fine. Okay. Yeah, so this seems to be a nice exercise. And before we do this, let's step back a little bit, take a look at the picture and yeah, see what we've done. We have reversed a more complex Java code based on Smali. So we reconstructed the Java code out of this. And this is pretty amazing in my opinion, because we already start learning Smali and we can already resolve complexer method names or method tasks over here. So in my opinion, I'm super impressed where we are at this moment right now. And I hope you feel the same. Otherwise, don't be worried, we increase the tempo later on, so we will do even more fancy and advanced stuff. But for now, let's enjoy this moment and insert those values, some kind of exercise work, and afterwards we go through this together. Have fun and I will see you in the next video.